Hi, my name is Rhiannon Ryan,
I'm Tiffany Godoy.
I'm Lisa Chung.
and today we are going to be presenting on our new EVA spacesuits that are meant to enhance the support for astronauts. Our mission objectives for this project are one, to enhance astronaut safety, two, to improve the system reliability, and three, to optimize mission performance. For enhancing the astronaut safety, we plan on implementing fine mesh sensors in the spacesuit, which will provide the continuous monitoring of data and to make sure there's nothing that's entering without when it should not be. We are going to improve the system reliability by maintaining the integrity and the efficiency of the LCVG, which is the liquid cooling and ventilation garment. And finally, we will optimize the mission performance by using our integrated advanced lower power sensors that will give us seamless data connection. So there was a story that broke the news, and it was that an astronaut who was in space had a spacesuit leak, and the astronaut almost drowned. We never want this to happen again. Our goal is to make sure that it doesn't. What we're going to do, and this is the motivation behind it, ensuring safety. What we're going to do is have a new mesh sensor system in a suit that will make sure that it tells the astronaut, alert the ground and the astronaut itself, that if there's any unwanted substance, if there's any temperature that shouldn't happen, and if there's any liquid that's seeping through. We want to improve the safety and allow the crew to know what's going on.
So these are the 5 key stakeholders we've identified for this project, and they include aerospace companies, space travelers, space agencies, academic institutions, and biotech companies. And based on these stakeholders and their values, we derived a list of values for our projects, which are listed below here from 1 to 10. And of these values, the ones that are not compromisable for our projects are safety, reliability, mobility, and compatibility with current spacesuit designs. Next.
Here we have our values and technical requirements put together. So for requirement 1, we are ensuring that malfunctions are detected immediately and accurately within a plus or minus 2% rate. For requirement 2, we are ensuring that the crew is notified immediately and have time to respond to any incidents within 5 to 10 seconds of occurrence, and notification within 2 to 5 seconds. For requirement 3, we are ensuring that the sensor system is fully functional in the space environmental conditions and inside the spacesuit. And we have our listed temperatures and pressures that it must operate and the time frames. And for requirement 4, we have compatibility and integration. This is to ensure that the new system, their new spacesuit can be generated and does not require as much training time to use. Requirement 5 is for communication and security. This is to ensure that information is transmitted by the system is clear and reliable, and it falls within these timeframes. And for our requirement 6 is our wearability. So sensor system must not place more limitation on the user's movement and any weight burdens as well.
This is the concept of operations for our projects. So first, the user will put on our spacesuit, and the sensor system within our spacesuit will constantly monitor conditions within the valves and filters of the ventilation system, and it will send these data to a processing unit, and this processing unit will then determine if there are any abnormalities, including clogs or leaks. If so, the processing unit will send a warning that will be displayed on the astronaut's helmet. The astronaut can then respond accordingly, ensuring their safety. The spacesuits will be stored and charged on racks inside the space station, and the spacesuit will then be disposed after 15 years or after the spacesuit fails beyond maintenance. Next slide. This is our architectural diagram for our project. As you can see, we divided the system into 4 main subsystems, including the sensors, the processing system, communication system, which displays the warning messages, and the storage systems. And the subcomponents of those systems are shown here.
So here we have our first proposed concept, which is the flexible liquid sensors to monitor fluid dynamics in real time, ensuring the cooling system functions correctly and efficiently. It can detect any fluctuations and potential leaks, and their flexible nature allows for integration into various parts of the suit, including the liquid cooling and ventilation garment, and comfort is not compromised. Some advantages is that it is flexible and can conform to the shape and movements, and it could be wrapped around or integrated into complex shapes, offering extensive coverage and more data points for monitoring. Some disadvantages is it may require special handling and calibration due to their flexible nature, and it is more susceptible to external damage or interference. Next slide. Here we have our chosen concept number 2, which is our fine mesh sensor. It provides a detailed measurement of the coolant flow and the pressure because it is directly attached to those openings, and it detects any leaks early on and can identify anomalies in the flow patterns. It can also monitor the coolant flow rate and ensuring the suit's temperature regulation system operates efficiently, as well as aiding in dynamic adjustments and preventative maintenance, enhancing the suit's performance and reliability. We have decided to go with this option because of our assigned values, including a target weight for the system, minimizing information processing time, minimizing accidents and malfunctions of the system, and ensuring minimal motion restrictions, all that came from our QFD. Here we have some advantages that are, it is highly detailed. It can provide highly detailed data and can capture small changes and detect minor leaks. It is more robust and less prone to errors from physical deformation. And some disadvantages is that it's more susceptible to clogging, reducing their effectiveness and accuracy over time, and may require regular cleaning or replacement. So we are overall aiming to revolutionize EVA spacesuit design, and here we have our basic parameters for characterizing system design choices, such as size and mass. We have our power requirements, material choice, and communication bandwidth. We have considered all of the parameters and timeframes and pressures and communication bandwidths listed here. Here we have our basic performance metrics, so how we are going to measure that our spacesuit actually works. So here we have data accuracy, operational sustainability, reliability and maintenance, and communication reliability. And here we have our equations connecting parameters with quantities of interest. We have our data accuracy equation, power efficiency equation, operational longevity equation, and our signal integrity equation.
As for our failure modes, things can often go wrong with spacesuits. The different types that can go wrong are sensor malfunctions, which has a major impact, mesh integrity failure, major impact, data transmission failure, major impact, and power supply depletion is a critical impact. As for the sensor malfunction, we can help. All of these are also technological failures. To help approach and manage these faults, for sensor malfunctions, we can have a ton of sensors. For mesh integrity failure, we can use higher durability materials. For data transmission failures, we can have communication protocols and backups. And for power supply depletion, our goal is to develop low power sensors and to integrate more energy efficient storages for said power supplies inside of the suit. And the cost impact is moderate for sensor malfunction, moderate for mesh integrity failure, high cost impact for data transmission failure, and a critical cost impact for power supply depletion. And that one has the most critical impact because it's a loss of all the system functions.
So here we have our first risk, which is technical feasibility. Given that this fine mesh sensor technology may not be sufficiently advanced, we have decided that we need to, for a mitigation strategy, require extensive prototyping, modeling, simulations, as well as staffing with sensor technology experts. We have rated this as a likelihood of rare and a consequence level of pretty catastrophic if the risk mitigation strategy fails. For our second risk, we have the cost overruns, given that this concept might be highly cost intensive. So our mitigation strategy would be to implement a phased funding strategy and strict budget management with frequent cost benefit analysis. We have ranked this likelihood of pretty unlikely and a consequence of critical. For risk number 3, we have supply chain issues. Sourcing material and components may be difficult and may lead to developmental delays. So our risk mitigation strategy would be to establish backup suppliers, developing contingency plans, and maintaining inventory buffers and reusing parts. We have also ranked this likelihood as unlikely and consequence of critical. For our 4th risk, we have regulatory and safety compliance. Given that this is a new spacesuit, it must meet all of the already strict and safety regulatory standards, and there is a possibility of non-compliance, which will lead to project failure. So our risk mitigation strategy would be to meet with regulatory stakeholders in the early stages, conduct frequent project check-ins, and ensure compliance throughout the entire development. This likelihood is pretty rare if we were to follow the mitigation strategy, and the consequence would be catastrophic. And for our last risk, we are addressing the environmental testing failures. So given that the spacesuit and sensors must withstand harsh space environments, there is a possibility of failure during environmental testing that may break the spacesuit in general, thereby leading to redesigns and increased testing requirements. So our mitigation strategy would be to develop pre-flight testing to simulate space conditions and continuously test the parts quality, as well as using material and components that are already approved to be space durable. So the likelihood of this would be pretty unlikely, and the consequence would be critical.
So for our cost estimation, we used a bottom-up model that estimates the cost of each very detailed subcomponent. And for the non-recurring costs, we estimated the total cost to be around 3.6 million. Next slide, please. And for the recurring cost, we estimate the total cost to be 361,000 for each spacesuit. Next slide, please.
So in conclusion, if we are able to, and when we are able to develop this spacesuit that has these fine mesh sensors that will allow real-life monitoring of the LCVG, it will represent such a significant stride in the aeronautical and astronautical field, as well as ensuring the safety of our astronauts. Next step is prototyping and testing. We want to create prototypes for this integration and functionality and comfort, and to simulate it in space environments to make sure that under pressure it does not crack. And we want to conduct extensive tests in the real world and space environments. And as soon as we get those results, we will refine the suit and do what's necessary. Thank you so much.
Thank you.
Thank you.